Hello NET aspirants. Welcome to CSIR NET Electromagnetic Theory series. Question number 1. A 1 kilometer long optical fiber of core and clad refractive indices 1.62 and 1.52 respectively is laid in a straight line. Several identical light pulses are launched simultaneously from air on the entrance of the fiber from different angles about its axis as shown in the figure. The diameter of the fiber is small compared to its length. The maximum time difference between the pulses emerging at the other end of the fiber would be close to. Now the time taken by light to travel through the fiber of length L will be T is equal to L by V, that is here velocity in the medium, which can be written as C by N, where N is the diffractive index. Now maximum time difference between the pulses traveling through the core and through the clad, that will be equal to delta T, and that is T into refractive index of core by C minus L refractive index of clad by C. That is L is given to us 1 kilometer, which is 1000 meter, upon C is 3 into 10 to the power 8, and difference will be 1.62 minus 1.52, which is 0.01. So if we solve this, this is 333 nanoseconds. So option 1 is correct. Next question. A plane electromagnetic wave is incident normally on a perfectly reflecting mirror in a vacuum. If the permittivity of free space is epsilon naught, the force exerted on an area A of the mirror would be. Now for a reflecting mirror, pressure is equal to 2I by C, where I is the intensity of electromagnetic wave in a vacuum, which is equal to half epsilon naught C and magnitude square. So here magnitude of electric field square. So the force will be equal to pressure into area. That means this will be equal to 2 by C 1 by 2 epsilon naught C EI square into area. So this is equal to A epsilon naught EI naught square. Now this is the force exerted on the mirror. It is in opposite direction to the direction of incident wave. So this will be equal to, this force will be equal to minus of A epsilon naught EI square Z cap. So option 4 is correct. Next question. A circular loop of radius A in the xy plane and a square loop of side B in the xz plane are kept at a distance r. Both carry current I as shown in the figure. If r is much greater than A and B, the torque exerted on the square loop by the circular loop is. Let's first of all calculate magnetic moment of the circular loop. That will be equal to current into area, so that is I pi A square, and it will be in the z cap direction because it's like this, so z cap direction, perpendicular to the area. Similarly, magnetic dipole moment due to square loop, that is ms, that will be equal to current into area, which is b square, and it will be in loop like this, so it will be in minus y cap direction. Now the magnetic field B due to magnetic dipole moment mc at point on the y-axis at a distance r, it can be written as B is equal to mu naught upon 4 pi 1 by r cube, then we have 3 mc dot r cap minus mc, where r cap is equal to y cap. We want to find out at this point. Now mc is along z cap direction and r cap is along y cap direction. That means mc dot r cap is equal to 0 because this is z cap dot y cap. That means magnetic field will be this part only. So this is mu naught then into minus mc upon we have 4 pi r cube. So this is the magnetic field. Let's substitute value of mc also. This is mu naught upon 4 pi r cube into I pi a square z cap. Now the torque on the magnetic dipole moment in a magnetic field is equal to ms cross b. ms. And we have the expression for ms and also magnetic field. So we'll just solve it. So this is minus sign is there. So this will be equal to I b square y cap cross minus mu naught 4 pi r cube I pi a square z cap. So we have y cap cross z cap, that is minus x cap. So we have minus from this minus sign into 4 mu naught upon 4 pi r cube into pi a square b square I square, and then we have x cap, which is equal to option 4. Next question. In a particular inertial frame, electric field E bar and magnetic field B bar are given. Which of the following statements is true? Now we know Lorentz invariants for all the electromagnetic fields, that are I1 is equal to E dot B and I2 is equal to E square minus C square B square. So let's first calculate that. Here we have I1 is equal to E dot B. This is x cap, so this will be E naught square by 2C, which is not equal to 0. That means this electric field and magnetic field are not perpendicular to each other. So electric and magnetic field are not perpendicular. Second, we have E square minus C square B square, which is equal to I2. So let's take mod. So this will be E naught square minus E naught square by 4C square, which is equal to 3 E naught square by 4 into C square is also there. So again, this is greater than 0. If this is greater than 0, that means electric field dominates over the magnetic field. Now let's consider some cases. Suppose E bar is equal to 0. This implies that it is electric field will not dominate over magnetic field. That means this I2 will be less than or equal to 0, but which is not the case. And suppose B is 0. In that case, if B is 0, in that case I1 will be 0. But it is non-zero in our case. That means such an inertial frame will not be possible in which either E or B are 0. So option B is correct. A long cylinder of radius r carries a magnetization m, where k is a constant, rho is the radial distance from the axis, and phi is the azimuthal unit vector. The magnetic field inside and outside the cylinder would be. So here magnetization is given, which is k rho square phi cap. We can calculate volume current and surface current. So del cross m is equal to 1 by rho. So curl of m will first consider dou mz by dou phi minus dou m phi dou z rho cap plus dou m rho dou z minus dou mz dou rho phi cap plus 1 by rho dou by dou rho rho m phi minus dou by dou phi of m rho z cap. But only phi cap term is there, so mz is 0 and m rho is also 0. So finally we are left with this one term only, which is 1 by rho dou by dou rho of rho k rho square into z cap. So this will be 3 rho square k by rho, that is 3k rho by z cap. And surface current kb will be m cross n cap. So at the surface we have rho is equal to r. So this will be k r square phi cap cross rho cap, which is minus k r square z cap. So we have only these currents which are inside the cylinder and on the surface of the surface. So outside the current cylinder there are no net currents enclosed. So the magnetic field outside, that will be equal to 0, and the magnetic field inside, then it will be equal to mu naught into m, which is k rho square phi cap. So here option 2 is correct. Next question. A thin circular wire loop of mass m having radius r carries a static charge q. The plane of the loop is held perpendicular to a uniform magnetic field B along the z-axis passing through its center as shown in the figure. The loop, initially at rest, can freely rotate about z-axis. When the magnetic field is switched off, the loop starts rotating with angular frequency equal to. Now here electromagnetic angular momentum in the fields of a charge q distributed on a ring of radius r is given by q b r square by 2. So this is L electromagnetic. And mechanical angular momentum of the loop, that will be simply I into omega. And here I is for this ring, which is mr square into omega. Now when the magnetic field is switched off, the electromagnetic angular momentum is converted to mechanical angular momentum. So qb r square by 2 will be equal to mr square omega. That gives omega is equal to qb by twice m. So here option 2 is correct. Two identical cubes are shown in figure A and B. The magnitude of magnetic field at the center of the cube in A produced by the currents as shown is V naught. The magnitude of the magnetic field at the center of the cube in B will be. So here if we consider this side, this plane, then magnetic field will be in this direction. Let us assume its magnitude is B naught. Now let's consider this part again. Here the magnitude will be along y direction, so it is B naught y cap. Now for this particular loop, it will be along minus x cap direction. So we have B naught and then minus x cap. Now we will consider the other side as well. So this side. So here it will be along z cap direction. So plus B naught z cap. So this will be the total magnetic field at the center of that cube. And if we consider magnitude of that field, then this will be equal to under root 3 B naught. So here option 1 is correct. Next question. A beam of light along the z-axis passes through a quarter plate and an analyzer as shown in the figure. The fast axis of the quarter wave plate is aligned with the x-axis. The light intensity is measured by a detector placed after the analyzer. Consider two separate scenarios where the incident light beam is circularly polarized and B linearly polarized along the x-axis. If the polarization axis of the analyzer is rotated by one full cycle about the z-axis, the number of times the detector measures the maximum intensity in each case would be. So we have a quarter wave plate, and in the first case we have circularly polarized light. Now intensity I of theta is cos square theta minus phi, where theta is the analyzer angle and phi is the initial polarization phase. Now cos square has period of 180 degree. So the maximum occurs twice in 360 degree rotation. Now if we consider linearly polarized light, then quarter wave plate converts linearly polarized light along x-axis into elliptically polarized light, or it remains linearly polarized if the input is along the fast axis. So analyzer will measure intensity I of theta, and that will be equal to cos square theta. So again it will have period of 180 degree, so maximum will occur twice in 360 degree rotation. So here option 4 is correct. Next question. A gas of electrons with no source of scattering is placed in an electric field E bar and magnetic field B bar, where E and B are constants. The frequency at which the conductivity in the z direction given by the ratio of current and the electric field both in the z direction diverges. So E and B are given. So the equation of motion will be m dv bar by dt, that is equal to minus E bar plus V bar cross B bar. And here in the z direction it will be m dvz by dt minus E, and this is in z direction, so in z direction it will not have any component. So into Ez, which is equal to minus e raised to I omega t. So we have mvz is equal to minus e raised to I omega t upon I omega. Let us assume vz is equal to some vz0 into e raised to I omega t. In that case, we'll have m vz0 e raised to I omega t is equal to e raised to I omega t upon I omega, and finally you'll get vz0 is equal to minus e upon I omega m, which is equal to IE upon omega m. That will be vz0. Now conductivity in the z direction, that is Jz is equal to minus Ne Vz. This is current density, and conductivity will be equal to Jz by E. So that is minus Ne Vz upon E. But this is the expression for Vz. So if we substitute this, then we will get sigma z is equal to minus Ne square I upon omega m. That means it will diverge when omega tends to 0, when omega is equal to 0. So option 1 is correct. So these were all the questions from electromagnetic theory part from NET July 2025 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.